Good evening everyone, good evening. I welcome you all again to JEE Enthuse. I hope you all are doing good. So people, quickly let me know in the chats if I'm perfectly audible and visible to everyone. Yeah, let me quickly know in the chats if I'm perfectly audible and visible to everyone. Hello Bhumi, hi Veer, hello Aisha. Let me know, my dear people, if I'm perfectly audible and visible to everyone. Yeah? Let me quickly know in the chats. Just give me a second, guys. I'll be starting, okay? Just give me a second. Just give me a second. All right, people. So, as you all must be familiar with, tonight we are going to have the quick session from the chapter Chemical Kinetics, and I'll be discussing some important concepts here, right? So it's going to be a short and very quick session. Let's try to learn some important concepts in the form of questions from the chapter Chemical Kinetics, my dear people, okay? So before starting tonight's discussion, the ones who have just joined in, the ones who are new to the channel, let me quickly introduce myself first. Well, my name is Wassim, and I'm your chemistry master teacher right here on this JEE Enthuse channel, yeah? Well, the ones who have not liked the video yet, do like the video, share the video with your friends, do subscribe to the channel, and do not forget to hit the bell icon so that you get the notification of every single session which we take live on this JEE Enthuse channel, right? So do like the video, share the video with your friends, and do subscribe to the channel as well, okay? Perfect. Let me quickly know in the chats, my dear people, if all of you are super duper excited about this particular session as well. Yeah, I'm doing good, Aisha. Thank you. Let me quickly know, my dear people. I'm doing good, Aishwarya. Thank you. Thank you. Hello, Priya. Hi, Naveen. Perfect, guys. Perfect. So without wasting a lot of time, let's get going then. Let's get started with tonight's discussion with the first question, which is going to be on your screen now. A very simple and basic question this is, right? Let's have a look how this sort of a question is to be solved. A very simple and basic question this is. If the rate of appearance of O2 is 0.5 moles liter inverse second inverse, then calculate the rate of disappearance of N2O5, right? So first thing, I'm supposed to calculate the rate of disappearance of N2O5. If I ask you, how do we represent the rate of disappearance of N2O5, right? Since I'm talking about the disappearance, so I'll be starting with the minus sign, right? Change in the concentration of N2O5 divided by time interval dt. This is what we call as the rate of disappearance of N2O5, and I need to calculate its value exactly. As per the question, I need to calculate value of this particular term, right? And how do we get the value of this particular term, which I call as the rate of disappearance of N2O5? Well, in order to do that, I will be writing the differential form of rate for this particular reaction. Well, people, if you calculate rate of reaction with respect to N2O5, you will be starting with the sign minus, then 1 divided by stoichiometric coefficient of N2O5 is 2. It's going to be change in the concentration of N2O5 divided by dt. This term actually gives you the rate of reaction with respect to N2O5, right? Similarly, if I ask you, what is going to be the rate of reaction with respect to N2O4? Since N2O4 is a product, so I'll be starting with a positive sign. 1 divided by stoichiometric coefficient is 2. It's going to be change in the concentration of N2O4 divided by what? Divided by time interval dt, right? I can write the rate of reaction with respect to O2 as well. Correct? I can write the rate of reaction with respect to O2 as well. Since O2 is the product, so I'll be starting with the positive sign. 1 divided by stoichiometric coefficient is 1, so it's going to be d of O2 divided by dt. Perfect. Now, what all things are we given with as per the question? We are given with the rate of appearance of O2. Rate of appearance of O2 means d of O2 divided by dt. This is what we call as rate of appearance of O2. And in this particular reaction, whatever is the rate of appearance of O2, same is going to be the rate of reaction as well, right? Now we will have a look. Rate of appearance of O2, which I've represented with d of O2 divided by dt, it's given to me as 0.5 moles per liter per second, right? This is something which is given to me. What do I need to calculate? I need to calculate rate of disappearance of N2O5. So what I'll be doing, I'll be equating this term with this particular term, right? So I'll be writing minus d of N2O5 divided by dt, right? This 2 I'll take over here in the numerator. It's going to be plus 2 times d of O2 divided by dt. This term is what you call as the rate of disappearance of N2O5 and whose value I'm supposed to calculate. So it's going to be 2 multiplied by d of O2 divided by dt. That's given to me as 0.5, right? So the value comes out to be exactly 1 mole per liter per second. So this is something which I call as rate of disappearance of N2O5, and we got its value exactly as 1, right people? As simple as that. So option A is going to be the correct answer of this particular question. I'm sure you can easily solve these sort of questions, right? Perfect. Vedantu, you can watch both. You can watch both sprint as well as this one. Perfect, guys. So let's move on to one more particular question. Look at this one. Well, I'm given with a reaction that is 2 times NH3 gives N2 plus 3 times H2, right? This is the reaction that's given to me. What do I need to calculate exactly? I'm given with the concentration versus time curve as well. And for this particular question, I'm supposed to calculate rate of reaction in the interval 5 to 15 seconds, right? I need to calculate rate of reaction in the interval 5 to 15 seconds. If you look at this particular curve, people, the concentration is decreasing with time. The concentration is decreasing with time, right? And we know concentration of reactant decrease with time. So this curve is basically given for the reactant. This curve is valid for the reactant, and reactant over here is NH3. So basically this is the curve that is given for NH3, right? This is the curve that's given for NH3. Perfect. That's something which I analyzed first. Now, I need to calculate the rate of reaction in the interval 5 to 15 seconds. So in this time interval, I need to calculate rate of reaction. Perfect. So can I write rate of reaction with respect to NH3? Since NH3 is the reactant, I'll be starting with minus sign. 1 divided by stoichiometric coefficient, that's 2. Change in the concentration of NH3, right? Change in the concentration of NH3 divided by time interval, right, my dear people? So this term will be absolutely giving me the rate of reaction with respect to NH3. Perfect. So I'll be writing rate is equal to minus 1 by 2. Change in the concentration of NH3. I need to calculate rate in this time interval, 5 to 15 seconds. So this is the final concentration of reactant, and this is the initial concentration of reactant. So let me write it as final concentration of reactant, which is 0.2, minus initial concentration of reactant, which is 0.6, divided by time interval from here to here, it's 10 seconds, right? I would want you guys to solve this term and get the value of rate of reaction, that's it, right? So this term you need to solve, you need to do a bit of calculation, you'll be getting the rate of reaction from here. Okay, that's something which we were supposed to calculate, the rate of reaction. Perfect. So I'm sure you got to know exactly how to solve this question. So final answer of this particular question will be coming out to be 0.02 moles liter inverse second inverse. Right, my dear people? Let me move on to one more question. This is one more question that's given to me. What do I need to see? For the following reaction, some parameters are given. Find the relation between K1, K2 and K3. All right. I need to get the relation between K1, K2 and K3. How do we solve these sort of questions? It's again a very simple and basic question. See, the reaction that's given to me, let me write the differential form of rate for this particular reaction. I'll be starting with minus sign, change in the concentration of N2O5 divided by time interval, that's dt. It's going to be equal to plus 1 divided by stoichiometric coefficient. It's going to be change in the concentration of NO2 divided by dt, right? Which is also going to be equal to, stoichiometric coefficient is 1 by 2, so it's plus 1 divided by 1 by 2. So that 1 by 2 comes up, so it's going to be plus 2 times change in the concentration of O2 divided by dt, right? This is something which I wrote first of all, correct? Now guys, have a look. Minus times d of N2O5 divided by dt, this value is given to me as per the question, that's K1 multiplied by concentration of N2O5. So instead of this particular term, I'll be writing K1 multiplied by concentration of N2O5, right? Plus 1 divided by 2. d of NO2 divided by dt. d of NO2 divided by dt, that's again given to me as K2 multiplied by concentration of N2O5, right? Which can be written as plus 2 times d of O2 divided by dt is also given to me, K3 multiplied by concentration of N2O5. Now people, as you can see in this particular reaction, in this particular equation, N2O5, N2O5, N2O5 gets cancelled out. So finally I'll be getting something like this. K1 is equal to K2 divided by 2, which is going to be equal to 2 times K3, right? If I multiply throughout this 2, it becomes 2 times K1 is equal to K2 is equal to 4 times K3. So this is basically going to be the relation between K1, K2 and K3, which I was supposed to calculate, right? Yes? I'm sure it's clear to everyone, right? So the answer of this particular question is 2 times K1 is equal to K2 is equal to 4 times K3. So what is going to be the correct answer? It's going to be option B. I'm sure it's clear to everyone. Let me move on to one more particular question. Okay. Again, the similar sort of question, and I'm sure you can easily solve it now. For the reaction, half of A gives 2 times B. Okay, so first thing which I'll be doing, let me write the differential form of rate. So I'll be starting with the minus sign. 1 divided by stoichiometric coefficient over here is 1 by 2, so that 2 comes up. It's going to be change in the concentration of A divided by dt, which can be also written as plus 1 by 2 plus 1 divided by 2, change in the concentration of B divided by dt. What do I need to calculate? The rate of disappearance of A. I need to get the rate of disappearance of A. Okay, so rate of disappearance of A, I'll be writing it as minus times d of A divided by dt is equal to plus 1 divided by. This was already 2 over here. Now this 2 comes as the denominator, is going to be 4 d of B divided by dt. Right? So this is going to be the correct answer of this particular question. Rate of disappearance of A minus d upon dt is equal to 1 by 4 dB upon dt. So it's option B, which is the correct answer of this particular question. I'm sure this is again clear to everyone. Right, people? Let me move on to one more particular question. For a chemical reaction, again a simple question, my dear people. For a chemical reaction A gives B, it is found that rate doubles when the concentration of A is increased 4 times, right? So basically, the reaction that's given to me is A gives B, right? Let me write its rate law first of all. So rate of reaction is equal to K multiplied by concentration of A raised per order, and order of the reaction is N. Let's assume that, right? Now, let's call this as equation number 1 first of all. Let's call this as equation number 1. It is found that the rate doubles when the concentration of A is increased 4 times, right? So now it becomes 4 times A raised per N. Let's call this as equation number 2. As per the equation, I'm doing nothing. I'm doing whatever the equation says. Rate is getting doubled when the concentration is becoming 4 times, right? If I divide second equation with the first one, RR gets cancelled, so the value comes out to be 2. KK gets cancelled, it becomes 4 raised per N. So from this particular equation, you can say 2 is equal to 2 raised per 2N, right? So this particular equation is only true if 2N value will be equal to 1. So from here, N value is equal to 1 by 2. And what was N basically? N was the order of the reaction, right? So order of reaction exactly comes out to be half. So it's absolutely option D, which is going to be the correct answer of this particular question as well. Perfect. I'm sure this is again clear to you. Okay, look at this particular question also, my dear people. The question says, we are given with some data, right? 0.1 molar concentration of A, 0.1 molar concentration of B, rate of reaction, 0.1, 0.2, 1.2, 0.2, 0.1, 1.2. Just a second, you need to make certain changes in the question. This is not 1.2 over here, this is 2.4. This is 2.4 in 10 raised per minus 3, right? Now, how do we get the order of the reaction? Do we need to calculate the order of the reaction? See, we need to get the rate law. If I want to write the rate law, it's going to be equal to K times concentration of A raised to the power X, concentration of B raised per Y. X is what we call as order of reaction with respect to A, Y is what we call as order of reaction with respect to B, right? Now, people, if you look at the first and the second experiment, in which the concentration of A is kept constant. Concentration of A is kept constant. So let's omit this A from here. Concentration of A is kept constant. Now what am I doing? Am I doubling the concentration of B? Absolutely. On doubling the concentration of B, what is happening to the rate? Nothing is happening to the rate. So rate of the reaction, I must say, is independent of the concentration of B, right? Rate of reaction is independent of the concentration of B. Perfect. Now people, if you look at experiment number first and the third one, if you look at the first and the third one, in which the concentration of B is kept same, right? Concentration of B is kept same. The concentration of A is doubled, and this is 2.4 here, right? See, concentration of A is doubled, and rate over here is doubling as well. Rate over here is doubling as well. On keeping the concentration of B fixed, doubling the concentration of A, rate is getting doubled, which is only possible if the value of X over here is equal to 1, right? If the value of X over here is 1. Perfect. So on doubling the concentration of A, rate is getting doubled, right? Which is only possible when the power over here is 1. So I must say rate law is going to be R is equal to K, A key concentration raised per 1, right? Perfect. So this is option D, which is the correct answer of this particular question. Right, people? As simple as that. Let's move on to one more question. half-life for a zero order reaction is given to us as 1 hour, right? Let's say you have got the zero order reaction like this. A gives B. This is a zero order reaction. Its half-life is given to me as per the question. How much it is? Its half-life for a zero order reaction is 1 hour. Is 1 hour, right? When the initial concentration of reactant is 2 molar. So first thing which I'll be doing, I'll be calculating rate constant of the zero order reaction, which is A naught divided by T half, right? So just a second. I hope you know this expression. Half-life for the zero order reaction is equal to A naught divided by 2K, right? So I'll be getting the rate constant of the reaction as A naught divided by 2 times the T half. Well, the initial concentration A naught is given to me as 2 molar, right? Divided by 2 multiplied by T half, right? Multiplied by T half. T half value is given to me as how much? 1 hour. Perfect. So it comes out to be 1, right? It comes out to be 1 exactly. The value of rate constant is exactly coming out to be 1. Okay, or you can write its units as well, moles, liter inverse, hour inverse, right? So it's going to be moles, liter inverse, hour inverse. So this is basically going to be the rate constant which we calculated. Now we will have a look. What are we supposed to calculate as per the question? How much time does it take for its concentration to reduce from 0.5 molar to 0.025 molar? So how much time it takes for the concentration of A to reduce from 0.5 molar to 0.025 molar, right? I need to get this time interval. Right? Now, just to solve this question in lesser time, let me call this as A naught. Let me call this as initial concentration. Let me call this as concentration of reactant left at time t. So I need to get this particular time interval, right? So I'll be simply using the integrated rate equation for the zero order kinetics. It's going to be equal to AT is equal to A naught minus KT, right? So AT value is given to me as 0.025 is equal to A naught, I'm considering as 0.5 minus K value, you got to know as 1, right, multiplied by T. So from here, T you will be getting as 0.5 minus 0.025 and this value will come in hours, right? Okay. Was it 0.025 or 0.25? Wait, it's 0.25, right? It is 0.25 molar. So it's going to be 0.25 here. Okay, so T value will be coming out to be 0.25 hours. So this is basically going to be the time duration in which the concentration of reactant changed from 0.5 to 0.25 molar, which I was supposed to calculate. I'm sure this again clear to everyone, right? You can solve this question like this in lesser time, or else you can make two equations, right? And then you can eliminate the things and get the answer. That's completely your choice to choose the method. This is the simplest of all. That's why I showed this method over here, right? So let's move on to one more question then. A zero order reaction is 20% completed in 10 minutes. So let's say I've got the zero order reaction as A gives B. Let's say at time t is equal to 0, the initial concentration of reactant is A naught, right? Let's say at time t is equal to 0, initial concentration of reactant is A naught. Now, as per the question, a zero order reaction is 20% completed in 10 minutes. So after 10 minutes, 20% of the reaction is completed. That means after 10 minutes, 20% of the reactant has got converted into the products. If 20% reactant has got converted into the products, I must say 80% of the reactant will be still left in the container as such. 80% of A naught. This is going to be the concentration of reactant left after 10 minutes, right? Okay, 80% of A naught means 0.8 A naught. So this is the concentration of reactant left after what? After 10 minutes. Perfect. This is the concentration of reactant left after 10 minutes. As per the question, at what time the reaction will be 80% completed? At what time the reaction will be 80% completed? If the reaction will be 80% completed, what does that mean? That means 80% of the reactant would have got converted into the products. So 20% of reactant will be still left in the container. That means 0.2 A naught is going to be the concentration of reactant left at this particular time t. And this is t which I need to calculate. How do I solve this question, my dear people? See, I got two conditions right here. I got two conditions. I'll be putting both the conditions into the integrated equation and I'll be calculating this t over here, right? I'll be getting to know the time taken to complete 80% of the reaction. Perfect. Now, as you all must be knowing, as far as your integrated rate equation is concerned for the zero order kinetics, AT is equal to A naught minus KT. If I put condition number 1 in this particular equation, AT value is nothing, that is 0.8 A naught is equal to A naught minus K multiplied by T value is given to me as 10. So from here, you can easily get the value of K. K is going to be equal to A naught minus 0.8 A naught divided by 10. So it's going to be 0.2 A naught, 0.2 A naught divided by 10. So 0.02 A naught. This is the value of K which you got, right? Since it's a zero order reaction, it's going to be moles liter inverse and time is given in minutes and it's going to be minute inverse, right? So this is basically going to be, first of all, the rate constant. I'm not supposed to calculate the rate constant. I'm supposed to calculate this T over here. So in this particular equation, I'll be putting the second condition. As far as your second condition is concerned, AT value is equal to 0.2 A naught, right? Is equal to A naught minus K value we have already calculated, that is 0.02 A naught, right? Multiplied by T. I must say A naught everywhere gets cancelled out. So it's 0.2 is equal to 1 minus 0.02 multiplied by T. So T value over here comes out to be 1 minus 0.2 divided by 0.02. Solve this, it's going to be 0.8 divided by 0.02. Whatever value will be coming from here, that's going to be the time taken by the reactant to decrease its concentration from A naught till 0.2 A naught. That's something which I was supposed to calculate, right? Let me know in the chat if it is clear to everyone so that I can move on to the next one. It was a very simple question, my dear people. I made two conditions, right? From the first condition, I got the rate constant. From the second condition, I exactly got the value of T, right? That's something which I was supposed to calculate. Okay, so final answer after solving this question will be coming out to be 40 minutes, right? So this is the time taken to complete 80% of the reaction. That's it. Moving on to one more question. Look at this particular one. In what time will the molar ratio of ethylene to cyclobutane be 1? See guys, the question is simple. You have got the reaction as C4H8 gives 2 times C2H4. This is the reaction that's given to me. Well, it's not mentioned in the question whether the reaction is of zero order or first order. Check it out. The unit of rate constant is equal to second inverse, and you know, second inverse unit of rate constant is for the first order reactions, right? So this I'll be assuming as the first order reaction. Now first thing, at time t is equal to 0, let's say I've got A moles of this is going to be 0, right? Let's say at some time t, out of A moles of reactants, X moles got dissociated into the products, so I'll be left with A minus X moles of reactants at time t. Now 1 mole gives 2 moles, from X moles you would have got some 2X moles over here, right? What do I need to calculate? I need to calculate the time at which the molar ratio of these two becomes equal to 1, right? I need to get the time. I need to get the time at which the ratio of moles of C2H4 to that of C4H8 becomes 1. So this is T which I need to calculate. So basically I'm assuming this is the time at which molar ratio of ethylene to cyclobutane has come out to be 1, and when the molar ratio of ethylene to cyclobutane will be 1, at that point of time I'll say 2x is going to be simply A minus x, or you can say 3x is equal to A, or x value you can calculate as A by 3, right? So you got the value of x first of all. You got the value of x. Perfect. Now, simply use the integrated equation. You can say T is equal to 2.303 divided by K, where K value is given to us as 2.3 into 10 raised power minus 4, second inverse, right? Log of A naught by AT. A naught is the initial concentration, initial amount, that's A, divided by concentration of reactant left at time t, or moles of reactant left at time t. It's going to be A minus X, that's A minus A by 3, which comes out to be 2A by 3, right? 2A divided by 3. So A gets cancelled, it becomes log of 3 divided by 2, or you can write it as log of 3 minus log of 2. You can write it as log of 3 minus log of 2. Right? Well, log of 3, you guys know that is 0.47, log of 2 is 0.3. So 2.3 almost gets cancelled out. So 10 raised power minus 4 comes up. So this value will come out to be what? This value will come out to be 0.17. So the final answer is going to be 1700 seconds, right? So this is basically the time taken. This is the time taken. This is going to be the time at which the concentration, at which the molar concentration of products to that of reactants will come out to be 1, right? Or you can say this is the time taken at which the moles of reactants and products would have got equalized. Yeah, that's the point only when the molar ratio will come out to be 1. I'm sure it's clear to everyone again. Amritanju, all contains PYQs, all contains PYQs, right? I'm sure this question is clear, my dear people. So one more question is here. It's again simpler one. For a first order reaction, A gives products. The concentration of A changes from 0.1 to 0.025, right? in 40 minutes, the rate of reaction when the concentration of A is 0.01 molar. Say, the reaction that's given to us, that is A gives products. So A gives product, let's say that's B, okay? Now first of all, I'll be using the integrated rate equation for this first order kinetics, right? Have a look, people. For the first order reaction, the concentration of A changes from 0.1 to 0.025. Let me call this as A0 initial concentration. Let me call this as final concentration AT, right? Let me use the integrated rate equation. I'll say, just a second. I'll say K is equal to 2.303 divided by T. How much time does it take for the concentration of reactant to change from 0.1 to 0.025? It's 40 minutes, right? It's 40 over here. Log of A0. A0 is 0.1, AT is 0.025, right? So from here, you'll be getting the rate constant. And once you get the rate constant, you'll be calculating the rate of reaction as R is equal to K rate constant multiplied by concentration of A. Well, you need to calculate rate of reaction when the concentration of A is kept as 0.01. So A value, you'll be keeping 0.01 here, and rate constant value you would have solved from here. Put the value of rate constant here in this expression and get the value of rate of reaction. Simple question this again, right? Right, people? Right? I'm sure it's clear to everyone. So final answer of this particular question is going to be this one. I calculated the rate constant, which comes out to be 0.347 minute inverse. Then write the rate law. Okay, so that's how you write with the rate law. Put the concentration of A as 0 point something which is given, right? Put the rate constant and get the answer. That's it. It's again very simple and basic one. Okay, look at this particular question, my dear people. An organic compound undergoes first order decomposition. The time taken for its decomposition to 1/8 and 1/10 of its initial concentration are T1/8 and T1/10 respectively. What is the value of T1/8 divided by T1/10 into 10, right? This is again the simple question. Let's try to solve this one. See, let's say the first order reaction is A gives B. This is the first order reaction that's given to me. Let's say at time T is equal to 0, the concentration of reactant is A0, so absolutely this is going to be 0, right? Well, as per the question, T1/8, this is the time taken for the concentration of reactant to reduce from A0 to 1/8 of A0. To 1/8 of A0. That means right now the concentration of reactant left is going to be A0/8, right? And what is T1/10? T1/10 is the time taken by the reactant to change its concentration from A0 to 1/10 of its initial concentration, right? So this is the final concentration of reactant left at T1/10, right? Well, people, these are the two conditions which you got. These are the two conditions which you got. So what I'll be doing over here, I'll be using the integrated rate equation. As per integrated rate equation, if I write T1/8 is going to be 2.303 divided by K. It's going to be log of A0/AT. What is A0? Okay, A0 is the initial concentration divided by. What is AT right now at T1/8? It's A0/8. So this is going to be A0 divided by 8. 8 comes up, so it's going to be 2 raised power 3, right? 2 raised power 3 you can write as 3 log 2, right? You can write as 3 log 2. Simple. It's going to be 3 multiplied by log 2, and log 2 you guys will be knowing that is 0.3. So this is T1/8 you got first of all by using the integrated rate equation. Now if I write the integrated rate equation for T1/10, it's going to be 2.303 divided by K. Now it's going to be log of A0 divided by 80. What is the 80 value now? It's A0/10, right? It's A0 divided by 10. That 10 comes up. Log 10 is equal to 1, so nothing, right? So what I need to calculate exactly? I need to calculate T1/8 divided by T1/10 multiplied by 10. This value I need to calculate exactly, right? Well, people, T1/8 we got to know that is 2.303 divided by K, and it's going to be 3 multiplied by what? Multiplied by 0.3 whole divided by. What is T1/10? It is 2.303 divided by K, right? And multiplied with 10. This is multiplied with 10. So this term got cancelled. This will become 0.9. 0.9 multiplied by 10 comes out being 9, right? So 9 is going to be the answer of this particular question as well. I'm sure this is again clear to everyone, right? So 9 is going to be the answer of this particular question. Right, 9 is going to be the answer of, the final value of this particular part, right? That's something which I was supposed to calculate. I'm sure again it's clear to everyone. Let me move on to one more question. Look at this particular one. T1/4 can be taken as the time taken for the concentration of a reactant to drop to 3/4. to drop to 3/4 of its initial value, right? If the rate constant for the first order reaction is K, then T1/4 can be written as. T1/4 can be written as. See guys, it's again a simpler one. Well, the reaction, for example, is A gives B and it follows the first order kinetics, I believe. Is that? It follows the first order kinetics. T1/4 can be written as concentration of the reactant drops essentially the rate constant for the first. Okay, yeah, it's mentioned in the question that it follows the first order kinetics, right? Now people, at time t is equal to 0, let's say its initial concentration is A0. Its initial concentration is A0. So this is absolutely going to be 0 right now. Yeah, as simple as that. Now as per the question, what is T1/4? What is T1/4? T1/4 is a time taken for the concentration of reactant to drop to 3/4. So that means at time T1/4, the concentration of reactant left is 3/4 of its initial concentration. 3/4 of its initial concentration. So this is the concentration of reactant left at T1/4. What do I need to get? I need to get the value of T1/4 over here in terms of K, right? So I'll be simply using again the integrated rate equation. It's going to be equal to T1/4. I'll say T1/4 is equal to 2.303 divided by K. It's going to be log of A0 divided by AT. AT value is 3/4 A0, right? So it's 3 divided by 4 A0. A0 gets cancelled. It comes out to be 4/3. So you can write it as log of 4 minus log of 3. Right? You just need to solve this one. You'll be getting the answer. It's T1/4 is equal to 2.303 divided by K. Log of 4 is 0.6. Log of 3 is 0.47. Just solve this part. Get the value of T4. That's it. That's something I was supposed to calculate, right? Perfect. Right? Just solve this equation. Get the value of T1/4. And finally, T1/4 value after solving that equation will come out to be 0.29 divided by rate constant. That's K. I'm sure it's again clear to everyone. Let me know quickly in the chats, my dear people, if it's clear so that I can move on. So Sonanika, you can just drag the video a little back. It'll be a replay. Joshua, I've taken that session. You can check it out. Perfect. One more question that's given to us. And this is going to be the last question of the session, guys. As I told you, the session is going to be very short and precise, right? No, after this, I'll be solving 2 more questions, right? So after this, I'll be solving 2 more questions from the same chapter. For an elementary first order reaction, X gives Y plus Z. The reaction is X gives Y plus Z, right? T half is given to us as 10 minutes. Half-life is given. In what period of time would the concentration of X be reduced to 10% of original, right? So at time T is equal to 0, its initial concentration is A0, right? At what time the concentration of A will be reduced to 10% of its initial one. So at what time the concentration of A will reduce to A0 by 10, right? At what time the concentration of A will reduce to A0 by 10, right? Now first thing, it's not mentioned in the question whether the reaction is of 0 order or first order or second order or whatever. But it's mentioned that the reaction is elementary. And for elementary reactions, I'm sure you guys will be knowing, molecularity is always equal to order. So molecularity of this reaction is 1. So it's absolutely going to be the first order reaction, right? It's the first order reaction. Now, if it's the first order reaction, its half-life is given, right? I can say K is equal to 0.693 divided by T half. T half is 10 minutes, so value comes out to be 0.0693 and it's going to be minute inverse. This is the rate constant value which I got first of all, right? Now, I need to get this time basically. I'll be simply using the integrated rate equation. I'll say T is equal to 2.303 divided by K, and K value as per the question, that is 0.0693, and it's going to be log of A0 divided by AT. AT value is nothing, that is A0 by 10. So A0 cancel, log 10 is 1. Just solve this part, get the value of T in minutes, that's it, right? Get the value of T in minutes, that's something which I was supposed to calculate. I'm sure it's clear to everyone, right people? I'm sure it's clear to everyone. So this is the final answer which you'll be getting at the end. Okay, let me show you one more question, my dear people, just a second. Look at this one. A first order reaction is 75% complete in 100 minutes, right? Okay. Calculate the time in minutes taken for 87.5% completion. Well, I would want you guys to remember few results for the first order kinetics. Do remember, time taken to complete 75% of the first order reaction is 2 times the half-life of the reaction, number 1. Do remember, time taken to complete 87.5% of the first order reaction is equal to 3 times the half-life, number 2. Do remember, time taken to complete 99.9% of the first order reaction is equal to 10 times the half-life, right? Okay. Now, as per the question, first order reaction is 75% complete in 100 minutes. So this value is given to us as 100. If this value is 100, that means T half will be 100 by 2. That means T half is going to be simply 50 minutes. If you got the value of T half, 50 minutes, what do I need to calculate? I need to calculate time taken to complete 87.5% of the reaction. So I'll say time taken to complete 87.5% of the reaction is equal to 3 times the half-life, and half-life is 50. The value comes out to be 150 minutes. So you got to know exactly. So 87.5% of the reaction gets completed in 150 minutes. As simple as that. Similarly, you can calculate time taken to complete 99.9% of the reaction. It's going to be 10 times 50. 10 times the half-life. 10 times 50. That's 500 minutes, right? I'm sure it's again clear. Let's move on to one more, my dear people. This is one more question. For the first order reaction, choose the correct value of half-life. Okay, I need to get the half-life. Well, first of all, this is the curve that's given between log AT versus T, right? Well, I'm sure you guys must be familiar with this relation. Log of AT is equal to log of A naught minus K upon 2.303 multiplied by T. This is one more form of the integrated rate equation for the first order kinetics. Now you have plotted a curve between log of AT versus T. This was log of AT and this is T, right? So log AT versus T curve, what about its slope? Its slope is equal to minus K upon 2.303. So slope of this particular curve, right? Slope of this particular curve is equal to minus K upon 2.303. What is slope basically? Slope is basically tan of theta. What is theta? Theta is the angle which the curve makes with the positive x-axis in the anti-clockwise direction. That's 135. So tan of 135 is minus 1. So minus 1 is equal to minus K upon 2.303. So from here you got the value of K. If you got the value of K, you're supposed to calculate half-life. And you know, half-life for this first order reaction, that's equal to 0.693. 0.693 divided by K, and K you got to know as 2.303, right? Just solve this, get the value over here. That's it, right? That's it. Perfect. Perfect, my dear people. So final answer of this question after solving, you'll be getting it as 0.3 minutes. This divided by this is equal to 0.3 minutes, right? Simple? Absolutely. Okay, one more question, and this is going to be the last question of the tonight's session. Look at this one. What amount of reactant for the first order reaction will be left after 3.5 minutes? I need to get the concentration of reactant left. Concentration of reactant left is equal to A naught, which is the initial concentration of reactant, divided by 2 raised per n, where n represents the number of half-lives, right? This is one more expression valid for the first order kinetics. I'm sure you know it. Concentration of reactant left is equal to A naught initial concentration divided by 2 raised per n, and n represents the number of half-lives, which is given time divided by T half, right? Now first of all, is T half given to me somewhere? T half is not given to me, but I'm given the curve between ln of AT versus T. I'm sure you're familiar with the relation, that is ln of AT is equal to ln of A naught minus KT. So when you plot a curve between ln of AT versus T, when you plot a curve between ln of AT versus T, the slope of this curve is equal to minus K. So slope of this particular curve is equal to minus K. What is slope? Slope is basically tan of theta. What is theta? Theta is the angle which the curve makes with the positive x-axis in the anti-clockwise direction. So this is theta. If this is 45, this is 90, this is going to be 45, and this theta is going to be 135. And tan of 135 is minus 1. So slope is coming out to be minus 1. So you got the value of K exactly as 1, right? As 1 over here. And I'm assuming time is in minutes, right? So it's going to be 1 minute inverse. So rate constant K value you got exactly as 1 minute inverse. Okay. Now people, if you got the rate constant, can you calculate the half-life of this first order reaction? It's going to be equal to ln of 2 divided by K. Ln of 2 divided by K, and ln of 2 is, as per the question, we are supposed to take it as 0.7 divided by K value is 1. So half-life is equal to 0.7 minutes. If you got the half-life, I can calculate the number of half-lives. It's going to be equal to given time, that is 3.5 minutes, divided by half-life, that is 0.7. So n value will come out to be 5 simply. So I need to calculate the concentration of reactant left after 5 half-lives, right? Which is going to be equal to AT is equal to A naught divided by 2 raised per n, 2 raised per 5. 2 raised per 5 is 32. So this is basically the concentration of reactant left after 5 half-lives, which I was supposed to calculate. I'm sure you got to know how to solve this sort of equation, right? Okay. I'm sure people, a lot of things would have got cleared from here, right? So with this, I'll be taking a leave. This was a this was a very short and precise session from the chapter Chemical Kinetics, right? Okay, I'll be seeing you tomorrow at the same time. Till then, you take care. Bye-bye. God bless you all and love you all, my dear people. Take care. Bye-bye.